Hey everyone, thank you for joining me. I am Rishabh Changwani, and this is a ground robot designed to go where it's too dangerous for people, places like collapsed building, chemical spills, or wildfire zones. Um, Over the next few minutes, I'll walk you through how we've built, programmed, and tested this machine so it can explore hazardous sites safely and reliably. Imagine a city that's hit by an earthquake where buildings are shaky, there's gas leaks everywhere, and first responders can't rush in without risking their lives. What if we could send a robot instead? That's that is what is the core idea here. We needed a vehicle that can drive over rough terrain, sniff out dangerous chemicals, map out unstable structures, and send back critical data, all without putting any human in harm's way. So this presentation details the design and development of an unmanned ground vehicle for remote assessment of environmental hazards in post disaster scenarios. The system aims to maintain risk to personnel by enabling remote monitoring of hazardous areas through an array of environmental sensors and imaging systems that provide real-time data on atmospheric conditions. Post-disaster environments often contain toxic gases, unstable structures, high temperatures, and poor visibility, making them dangerous for human responders. While unmanned aerial vehicles have limitation to dense smoke, canopy cover, and where the conditions um, and adverse weather conditions, our AGV UV, our UGV platform offers a robust selection for ground level environment assessment. Moreover, the FAA restricts UAV operations in active disaster zones, particularly during firefighting efforts, creating a critical need for ground based solutions. We have packed this UGV with four game changing features. One is our CFD optimized sensor housing. We have used airflow simulations to shape the sensor board so that cameras and gas detectors stay cool and clear of dust. The housing system is such that it ensures accurate ground level air quality monitoring in turbulent environments. Second, we had to incorporate a redundancy on the communications part. So we have used a dual redundancy communications over here. First is we use a high-speed Wi-Fi link for big data and a backup XB radio for emergencies. So we are never cut off from the scenario. We have real-world validation, extensive field trials in post-disaster scenarios, and standard mobility testing. We've already run it in mock disaster tests and showing it can handle rubble and smoke. We have used an open architecture integration. That means we've built upon open architecture of environmental sensing, SLAM-based mapping, and web-based teleoperation using ROS and GStreamer libraries. Unlike existing commercial UG platforms that focus primarily on navigation or payload delivery, this system specifically addresses the critical gap in environmental hazard assessment for post-disaster response. Now, the system architecture is into four domains: hardware, components, the software stack, the communication, and power and control. Now, first starting with hardware, we have used a rugged 6 by 6 chassis, motor, gear, and suspension, as well as multiple sensor suites for environmental monitoring, 4 camera array, 360-degree camera coverage, and dual LiDAR for spatial mapping. On the software stack, we have a raw space stack, which is robot operating system with web-based dashboards for built using AngularJS, and the raw space stack that fuses sensor data, runs navigation, and serves the web dashboard. Each piece talks to the other over standardized interfaces, making the whole thing plug and play. Next thing, communication. We have a dual link setup with Wi-Fi for video and sensor data, and XP Pro radio frequency for low latency control commands and as a backup system. Next, power and control. We have used PID controllers for steering and velocity regulation with a 4 by 5 LiPo 6 battery pack, which is a 14.8 nominal voltage. Now, mechanical design and materials. We chose materials to balance weight, strength, and cost. Now, the UGV platform requires robust materials capable of withstanding harsh environmental conditions, including high temperatures, corrosive atmospheres, and mechanical stresses from rough terrain navigation. The chassis frame we have used is a 6061 T6 aluminum, which has a yield strength of 276 megapascals. The suspension arms is a 17-4 stainless steel. The sensor housing is a ULV9 rated ABS plate. And for the LiDAR, we have used a T300 carbon fiber composite. Now, why was the rationale to choosing such materials? A, the aluminum, which offers excellent strength to weight ratio and corrosion resistance. Stainless steel for superior fatigue resistance for suppression components. ABS because we needed fire resistance for sensor enclosures. And carbon fiber because it minimizes vibration transfer to precision instruments. Now to deep dive into the communication part of it and security part of it. In a disaster zone, we can't trust any one link. That's why we use dual radios, high bandwidth Wi-Fi for video, LiDAR and maps, up to 100 megabits over 200 meters line of sight. And for deployments beyond 250 meters, we could use any of the repeaters that are easily available in the market, and some antennas for extended operational range. We also used a XV Pro for control and telemetry backup, which is robust up to 500 meters. On top of that, we run point A to AES encryption, SSH tunnels, and TLS for all data. So it is difficult for a man in the middle to access our data. And this multi-layer security approach ensures data integrity and prevents unusual activity and vehicle control system. The sensor integration and housing. So our sensor suite includes a 360-degree LiDAR, a stereo camera, gas detector, and an IMU. We built a custom pod using CFD simulation to channel airflow across sensors, reducing dust buildup and overheating. This housing, it has press fit seals and a quick release lock so you can swap out modules in under a minute when a sensor fails or need calibration. The independent sensor array deployed at a strategic position, which is the first with the front bumper, the center roll cage, and the rear tray, provide special redundancy. Each array includes gas sensors, which are for carbon monoxide testing. Then we have the particulate matter sensor, the DH the DHT22 for temperature and humidity, and dual thermistors for localized heat detection. Now on the software side, we run ROS, which is a robot operating system on a mini PC. It fuses LiDAR and IMU data for SLAM-based mapping, maintains an occupancy grid, and publishes everything to a web dashboard, which is built using AngularJS. The operators see live 3D maps, sensor readings, and video feeds right in their browser or even at a tablet or at the command post. So now the web-based dashboard it is implemented using AngularJS and robot web tools with uh, tabbed panels for sensor metrics, vehicle control, camera views, and LiDAR visualization. The mapping and localization, we have used HectorSlam for 2D mapping using LiDAR inputs with 3D point cloud, which generates at 75,000 points per frame. For position estimation, we have used extended Kalman filter, also known as EKF, with fuses data from GPS and IMU, and wherever there is a LiDAR drift with under 1.5 meters over a 100-meter loop. Now, on the experimental results, range and latency, we tested communication range and delay in an open field. Wi-Fi stayed solid up to 250 meters with less than 220 milliseconds of round-trip latency. The XB control link worked out of a 500-meter 50 millisecond latency. These numbers ensure you can send big sensor data streams reliably while still having low latency fallback for teleoperation. The control channel using the Expo Pro radio frequency module achieved stable connection at a distance up to 1.2 kilometers under clear line of sight, exceeding the baseline requirements of 1 kilometer. The 5 gigahertz Wi-Fi link for high bandwidth data sustained stable transmission only up to 250 meters with signal repeaters and directional antennas being evaluated for future iterations. Now the latency performance, the video feed had a latency of zero 0.9 seconds. The sensor updates were given at 0.35 seconds, and the control signals took about less than 200 milliseconds via the XB extended ranges. These results confirm the system meets the design specifications and latencies under 1 second for critical feedback channels. Now, in the field trials, in our lab calibration, our gases sensors hit within uh, plus minus 5 ppb, and the LiDAR measured distances with a plus or minus 2 centimeter accuracy. We then ran two pilot deployments in a simulated chemical spill zone. The UGV mapped terrain, located leaks, and navigated through debris all autonomously and relayed results back without a single communication drop. The um, results are on your screen with all numbers, so I'm not going to bore you with that. Now, for power and reliability, we powered everything from a 22-volt 10 ampere lithium ion pack at which was running at 220 watt hours. At full load, the robot was drawing 5 ampere, giving us 40 plus minutes of runtime. We added watchdog timers and redundant power rails, so if one controller clashes, the other can limp home. In 50 plus hours of testing, we saw an uptime of 99.6% with only two resets needed, and both were handled automatically. The battery pack provides sufficient power for extended field operation. The runtime was 29.6 hours, which was ideal. Only sensors, it was 8.2 hours, drawing 1.8 amperes, and motors under load was 1.8, 8.5 hours with a current draw of 8 amperes. Under typical mixed use scenarios, the systems can operate continuously for 6 to 8 hours before requiring a recharge. Now, fault analysis and mitigation. The system reliability was evaluated through 50 hours of continuous operation, n is equal to 5 runs over here, to identify potential failures, failure modes, and validate mitigation strategies. For the LiDAR, failure mode was dropouts, and the rate was 1.2%, and it was auto reconnected with as a mitigation way. For the communication link, failure modes was jamming and interfering, and the rate was 0.8%. And the mitigation was we fall back to a 900 megahertz channel. For the MCU, we tried out brownout resets, and the rate was 0.5%. And as a mitigation, we added a watchdog timer reset. The implemented redundancy and automatic recovery mechanisms provided the majority of potential failure scenarios encountered during field testing. To wrap up, we've built a ground robot that can venture into risky zones, gather critical environment data, and keep humans safely back. Next steps: and future work include an AI-based scene analysis to flag hazards automatically, deploying swarms of these UGVs for broader coverage, and integrating satellite communications for truly remote operations. The key achievements were it had less than 5% deviation from calibrated references, reliable communication of up to 1.2 kilometers, and successful operation in harsh field conditions with 95 to 98% sensor uptime. The comprehensive power analysis enabling 6 to 8 hours continuous field deployment. For future enhancements, as I previously spoke about, extended operational range through mesh networking, implementing dynamic power management for extended missions, developing an even better autonomous navigation capability using 3D SLAM and reinforcement learning, and further reducing operator workload for fully autonomous operation in predefined hazardous zones. This system addresses critical limitations of aerial platforms in ground level hazard assessments, providing emergency responders with a safer and a more detailed alternative for disaster zone uh, reconnaissance. Thank you for your attention. I'd love to hear your thoughts or if you have any questions. Thank you.